Hi, I'm Konstantinos and I'm building an open source robot arm. Last video, we pushed motors like this one to their limits to figure out how much torque they can produce. And in this video, we'll be using that data to figure out the last part of our actuators, the transmission. Transmissions are used in mechanical systems to reduce their input speed. In our case, that's the speed from each motor, to produce more torque at the output. There's lots of different types of transmissions, but to simplify the ones that we'll be looking at, we can split them into two categories: rigid transmissions and flexible transmissions. The rigid transmissions most people are familiar with are the ones in manual transmission cars. These consist of gears of different diameters meshing with each other to connect the engine output to the wheels. The rigid transmissions most relevant in robotics are planetary gearboxes, cyclotral drives, and strain wave drives. The flexible transmissions most people are familiar with are probably chains on bicycles. They're considered flexible transmissions because the force travels through a flexible member, the chain. The flexible transmissions relevant to robotics are chain drives, friction drives or tendon mechanisms, and timing belt drives. Rigid transmissions are usually more compact and can transmit a lot of torque, but they also tend to be more expensive and heavier. They usually need to be lubricated, so they're sealed, but they're also quite well understood. In robots, these qualities make them well suited in locations that have high forces and require compactness. Flexible transmissions vary a bit more. They're usually lighter and cheaper than rigid transmissions, but they also require more space. This makes them ideal in robots when you have a lot of space or when you need the motor to be placed far from the output. A lot of times, flexible transmissions are used as the first stage of a reducer, with rigid transmission as the second stage. This hybrid approach allows a joint to have the design flexibility of a flexible transmission with the output rigidity of a rigid transmission. You can also have a gearbox and then a belt, but that's a bit less common because you don't get quite the same benefits. Because of these nuances, we'll be looking at both types of transmissions for each joint. Let's break down the ones we mentioned earlier. In terms of rigid transmissions, we have planetary gearboxes, which are cheap, they're very available, they have really high efficiencies, but they're also heavy. We have cyclotral gearboxes, which are very rigid, but also very expensive and really difficult to make yourself properly. And then we also have strain wave gearboxes that are also very rigid, but they're usually used for higher gear ratios. They're also really expensive and really hard to make yourself. Planetary gearboxes are the clear winner here for us. They're produced by many manufacturers in the NEMA standard sizes that are commonly used with stepper motors, so we'll have a lot to pick from. In terms of flexible transmissions, you have friction drives or tendon drives, which have very high rigidity, they're really light and very cheap, and can transmit a lot of force. But they're also really difficult to work with because the tendons usually require crimping or splicing to terminate, and they're also not as well characterized, so they would need a lot of testing. We also have timing belts, which also have high rigidity, they're light, they're easy to work with, and can carry high loads, and their prices are a little bit more than what you'd find in a friction drive, and their compactness is a little bit worse. Lastly, we have chains that can carry very high loads, and they're very rigid, but their price is just okay, and they're not quite as compact as belts or tendon drives, and they require relatively frequent cleaning and lubrication, so they're pretty high maintenance, and they weigh a lot. Here, the timing belt drives are the clear winner because we want a robust solution that's easy to work with, and we won't really need the high torque supplied by chains. Gates is the gold standard for belts, and they have some tools and catalogs to make belt selection easier, so I'll be using those. In both the rigid and flexible transmission categories, I could have chosen a slightly higher performance option by making it myself, namely the cyclotral drives and the tendon drives, but possibly an even larger factor than top performance is overall system reliability, which is what I'm going to get with an off-the-shelf planetary gearbox and a timing belt drive. And that's something that's worth a lot more than a marginal performance gain. If we take a look at the robot mockup from video 2, the two types of transmissions should make more sense. Here you'll see that sections 1 and 2 are pretty compact, sections 3 and 4 have plenty of space, and sections 5 and 6 are also pretty compact. Importantly, sections 1 and 2 are by the base of the robot, which is the farthest away from the payload, so they'll have to output the most torque. This isn't by any means the final design of the robot arm, but the general dimensions will be similar. Because of this, I expect roughly the following breakdown. Joints 1 and 2, we're probably going to use a timing belt and planetary gearbox hybrid. Joints 3 and 4, probably a 2-stage timing belt reduction. And joints 5 and 6, 2-stage planetary gearboxes. Very roughly based off the geometry of the mockup, I figured out the critical dimensions for the positions of the joints relative to the base. This allowed me to make a torque budget to get a better understanding of how much torque each joint will have to produce. This might seem obvious, but every joint in the robot not only has to lift the mass of the payload, but also the mass of each joint between itself and the payload. So I started doing the math at the end effector instead of the base. For each joint, I calculated how much torque a motor with a 20-to-1 reduction would need to produce to lift all of the mass between itself and the payload. That way, I could figure out what size motor to use there based off the chart that I made in the motor testing video. That gave me a solid estimate for the mass of that joint, and then I just repeated the process for all 6 joints. This math is done assuming the worst case scenario. Basically that everything is cantilevered at 90 degrees, but I still added 20% of the mass of each joint, and then on top of that, I derated the motor's continuous torque by 25% to give myself plenty of headroom. These are the motor sizes and reducers that I came up with. Joints 1 and 2 will have an 8108 size motor with a belt drive and then a planetary reducer. Joint 3 will have a 6208 size motor with 2 belt stages. Joint 4 will have a 4108 size motor with 2 belt stages, and joints 5 and 6 will have 4108 size motors with 20-to-1 2-stage planetary reducers. It's worth noting that for joints 3 and 4 that use 2 belt drives, the larger reduction happens first. That's because larger reduction ratios require a smaller input pulley, and smaller pulleys cause more stress in belts because the bend radius is smaller. The first stage is the one with less tension, so it makes more sense to keep the second stage reduction lower since it'll be under more stress. In joints 1 and 2, since we're going with a belt and gearbox hybrid, that's not as important, and a 5-to-1 ratio is more common than 4-to-1 in off-the-shelf gearboxes. But if we end up finding a low-cost 4-to-1 gearbox, we'll probably change the belt stage to be a 5-to-1 reduction. Another nice thing about timing belts compared to other options is that you can easily make production-level sprockets and pulleys by 3D printing them out of nylon and polycarbonate. I'll be 3D printing a ton of parts over the next few weeks to prototype the arm, and my 7-year-old 3D printer isn't really going to cut it, so I put together a Prusa Core 1 printer last week. I chose the Core 1 partially because I think it's the best printer at this price, but also because it's open source, and it just feels right to use an open source 3D printer to make an open source robot arm. At this point, most of the parts for the arm have been picked. I thought that I would have to do a bunch of testing for the transmissions, just like I did with the motors, but since the parts I was able to find come with a bunch of testing information already, there's a much lower risk of something going wrong compared with the motors. Now all I have to do is a bunch of designing, making, and breaking things to get to a working prototype. So hopefully next time I see you, there will be a working prototype on my desk. That's when the real testing is going to begin, so drop a comment with something you'd like to see me test with a finished robot arm. See you in a few weeks!